Yellowstone National Park in Wyoming is well known to have the most wide-ranging, numerous, and diverse geothermal features of any volcano on the planet. And especially unique is the fact that this caldera volcano contains the single highest concentration of geysers on the planet, with 465 active geysers among the 1,283 total geysers in the park during an average year. With such a vast total, comprising more than half of the planet's active geysers, it is an area which no geologist should ever miss. But, this begs the question, if Yellowstone has the most active geysers in the Northern Hemisphere, where in the world has the most geysers in the Southern Hemisphere? If we are going by the total number of young geysers in a geothermal field, then our answer takes us to an area very high in the Chilean portion of the Andes mountain range. There, 95 kilometers east-northeast of the city of Calama, El Tatio geysers at an elevation of 4,267 meters or 14,000 feet is the spectacular geothermal and geyser field known as El Tatio. In this volcanic geyser field there are approximately 110 geysers of various shapes and sizes, of which 80 are considered to be active at the present. These geysers are spread across a 30 square kilometer geothermal field, albeit in three main clusters, occurring alongside many hot springs, mud pots, mud volcanoes, and fumaroles. Altogether, this spectacular area which is at such high elevation that water boils at a mere temperature of only 85.5 degrees Celsius or 185.9 degrees Fahrenheit comprises 38.9% of all of the Southern Hemisphere's geysers. Surprisingly, these geysers for the most part are fairly short when compared to other world geyser fields, generally not reaching above 1 meter or 3.3 feet in height, with the tallest active geyser at the present only reaching a height of 8 meters or 26.2 feet high. So, why exactly does such a vast geothermal field exist here at such high altitudes? The answer involves the planet's largest known magma Altiplano Puna magma body chamber in addition to a volcano primarily situated across the border with Bolivia. First, let us discuss the world's largest magma chamber which underlies this entire geothermal field at a depth of 14 to 20 kilometers. Known as the Altiplano Puna magma body, it contains 500,000 cubic kilometers of molten rock. This massive body of magma has existed for 11 million years, forming in response to the Nazca Plate suddenly snapping downwards at a much steeper angle. As this occurred, a large portion of the underlying lithosphere detaches, causing tremendous volumes of magma to rush upwards into the crust. This has powered many large-scale caldera-forming eruptions, but also regional stratovolcanoes. For reference, the El Tatio geothermal field has existed since it formed 27,000 years ago, with its geothermal features continuously active in the time since. Well, this 27,000-year figure is quite interesting. You see, this is nearly identical, or at least close to the margin of error for the last eruption of the Tocorpuri volcano 17 kilometers to the southeast. And I do not believe that this is a mere coincidence. That last eruption 34,000 years ago emplaced a massive 1,000-foot tall steep lava dome with a volume of 4.7 cubic kilometers of rhyolite lava. I would like to suggest that this magma was sourced from the Altiplano Puna magma body, but that a portion of the intruding magma stayed at several kilometers depth and did not erupt, remaining there and still slowly cooling at the present day. Thus, both this body of cooling magma and the much deeper Altiplano Puna magma body act as heat sources which heat regional groundwater to steam, forming various geothermal features and geysers at El Tatio. This groundwater originates in a region on geothermal pathway and in the basin directly north of the Tocorpuri volcano, seeping into the ground from heavier than average regional precipitation and going as much as 2 kilometers underground. It then utilizes a series of strike-slip fault underground, traveling at an average rate of approximately 1 kilometer every year. It then reaches a series of normal fault lines and the edge of a graben which forces the heated groundwater upwards, causing water to gush onto the surface as various geysers. The entire journey this groundwater takes lasts an estimated 15 to 20 years. As a final note, I would like to thank my new YouTube channel member Zach Brun for supporting my